Hi everyone, I'm Jin Yang, a master's student from National University of Singapore. It's my great honor to present our team's work, HasRL Robot, a heterogeneous asynchronous reinforcement learning system for high-dimensional bipedal control at APSIPA ASC 2025. So let's get started. First, let's focus on two general stages in reinforcement learning: data collection and policy optimization. In the first stage, agent interacts with the environment, and the interaction process, that's to say, interaction trajectories, will be collected and then utilized in the second stage for backpropagation. The problem is the running speed of policy updates generally fast, thanks to graph computation, but the data collection phase is relatively quite slow, where the difference can be hundreds of times. This motivates us to think if we can parallelly collect data in the stage 1, and then transfer it as a bench to stage 2. For the middle of them, we put a buffer. And for stage 1, we can keep it on the CPU, especially when the RL simulator can only support running on the CPU. And for stage 2, we can put it running on a more powerful device, GPU. We believe this framework can achieve not only computational effectiveness, but also a wider data distribution compared to a single environment, so as to enhance the generalization capability of policy. Here comes the method to realize our idea, and the overall framework is shown as follows. During each iteration, each parallel simulation workers contains an agent interaction with the environment, storing collected trajectories into their buffer first. Then, a centralized buffer accumulates trajectories from multiple workers until reaching a preset time step threshold. Once the buffer is full, the collected data will be transferred to the GPU and be organized into benches for updating the policy and value network. After that, in the next iteration, all agents act based on the same latest updated policy parameters. Next, I will hand over to George and talk about details of the implementation.
Here we define the structure of our reinforcement learning agent implementation. The state base is 50-dimensional. It includes previous states, position, and velocity about accurate joints and passive joints, phase clock signal, and target speed command. The action space is 10-dimensional, corresponding to the continuous control commands for the robot joints. For the actor network, we use two STM layers followed by a fully connected layer, and it outputs a Gaussian distribution over actions, which provides both flexibility and exploration capability. The critic network is implemented with three fully connected layers. It generates the value function, helping the agent evaluate the quantity of each state. The reward function is designed to encourage stable and gate-synchronized working, while penalize unstable motion, efficient torque usage, and abrupt control signals. Stability is primarily evaluated through previous related components, since the previous reflects overall posture and balance. To enforce gate synchronization, footfalls and velocity terms are modularized by sinusoidal clock signals aligned with the locomotion phase, rewarding timely connect and liftoff. During training, the policy performance improves step by step. The training return rates from 5 to 12.5. The evaluation returns peaks at 40 and stays stable. It shows good generalization without overfitting. Entropy is high at the start and pushes exploration. Later it goes down and the policy becomes more certain. The PPO clipping ratio is large at first, then it converges between 1 and 2. This keeps the upstate stable. A higher learning rate makes upstates stronger. Over large learning rate may cause instability. We need a balance between fast learning and long-term performance. The video shows the result of our training. Cassie walks forward in a stable way, the legs moves in sync, so the gait looks smooth. The controller is robust, and the robot maintains good balance.
Finally, here is a summary. Our findings highlight the importance of addressing the data collection bottlenecks in high-dimensional RL and show that heterogeneous hardware utilization can lead to substantial gain in learning throughput. That's it. Thank you all for listening. And here is the code and our contact. We will be very happy to hear from you. Feel free to raise any issues on our GitHub repo and just reach out to us via LinkedIn or email.